Let's look at vacuum tubes and transistors. So to understand what's the difference between them, let's look at what they do. So actually, they do the same thing. They amplify signal, and they do it using actually a very similar thing. So both of these have three elements inside. So for a transistor and for a vacuum tube, both of them, they need three things. So they need an anode, and they need a cathode, and they need a control element between them. So here we have these three things. We have an anode and a cathode and a control element between them. And here on the vacuum tube, if you look at it, if you can see in the middle, so those two wires in the center, that's the cathode. And the one you see, that tiny piece, that's the support rod for the control element, and that's on the other side, that's the support rod, and that gets connected into one of those small tube pins. So that's the control element, and the big one that you can see, that's the anode, and it's also called a plate in a vacuum tube. The cathode is called a cathode. In case of a direct heated triode, which this is, it's also the filament, but we'll get into it what a filament is, because that's something different. So transistors do not have filaments. So we cannot see the inside of a transistor because it's covered up in a chassis. All we can see is that there are three legs, plus there's this metallic part that we can mount to a heatsink. So we attach a heatsink so that sinks out the heat. So the heat is dissipated, it's transferred away from the body, so you can use it for higher power compared to without a heatsink. For a vacuum tube, it's the large glass surface of the bulb that's conducting the heat away from the tube, and there are heat sinks for vacuum tubes as well. And they actually, what they used to do in broadcast is they submerge the vacuum tubes in a liquid bath, and they circulate that fluid, and the fluid that conducts away the heat, and that can act as a tremendously strong heat sink. If you don't want to go to those extremes, you can blow air on the tube, on the glass, and cool the tube tremendously. But you can also add like a simple heat sinks, which is basically pieces of copper, surround the bulb with copper and blow air at it, and then the heat transfer will be much better, because copper is much better at transferring heat than the glass is. So anyway, so for both of these devices, when they operate, they generate a lot of heat, and if you heat sink them, one thing, they can attain much greater power, and two, they live much longer. And both of these devices, so both a triode and a basic transistor, they have a cathode, which is an electron source. So the electrons go from the cathode towards the anode, and there's a control element. So this has different names for the transistor and for the vacuum tube as well. But how do they function? How do they achieve this? The array of these three electrodes is completely different in the case of these three. So in the case of a transistor, these three elements are achieved so that they use something that's called a semiconductor. So it means that you have a piece of silicon, and for that piece of silicon you basically divide it into three parts, and one of the parts you either add elements to the silicon that's that adds extra electrons, like for example like a phosphorus that adds an extra electron, and to the other two you add something that has one electron less, so it has like a gaps introduced, and you add for example aluminum atoms there. So you have a silicon based substrate doped with aluminum on these sides and doped with phosphorus, for example, or you can reverse the order, so it's either NPN or PNP. So basically you are adding electron and then holes, or adding holes and electrons, vice versa. And because of this configuration, there is no conductivity between this element and that element. The electrons cannot flow from that direction to there. So when we would put a transistor into a circuit, then we would add, so like this would be a battery, and then we would have the current running through there. And the current cannot run if there is no voltage applied to the middle leg. And when there's a certain voltage applied that reaches a critical threshold, then we start to see electrons moving across this circuit. But unless that voltage is applied, nothing is happening. So basically we have this situation that here we have one electrode, two electrodes connected to the circuit, and there's a third electrode that is physically connected to the other two, that is blocking the path of the current. And when we apply voltage here, then this block gets less and less and less, and depending on the voltage we add here, we are multiplying the current. So basically a transistor is a device that if we, for example, apply here like 1 milliamp of current, and let's say maybe this is added through here like 1 milliamps, and then it will result in a 20 milliamp current around here. So basically we are multiplying current. Transistors are current multipliers. However, their inherent limitation is that the effect of this control element, so this is kind of like a control rod in a nuclear power plant. This control element is physically connected, and the boundary, the interface between these two electrodes, that's a chemical interface, and it changes depending on the voltage applied to the control electrode. And whenever you change your signal, the boundary between these elements and between these two elements, the properties of that boundary change. So we've got a limitation there, that there's an electrochemical reaction happening between these elements. In the vacuum tube, you do not have that situation, because there what we have is we have the anode. So let's say this is our anode, and that's the control element, which is called the grid. And then we have the anode, and in case of direct heated tubes, they write the anode like this, like a U shape. And here let's say if you put this into a circuit, then it would be like this, like a battery here, and we are closing the circuit. So there is current flowing through here. However, if we apply voltage to the grid, negative voltage, then we shut down the flow of the current. So based on the voltage we apply to this control grid, that's how we can either the current flows or it's cut down. But let's see what's the difference between this situation and that, because until now it seems that the tubes are doing the same thing as a transistor. However, the huge difference that here, these three elements are not physically connected. These elements are separated from each other and they are inside a hard vacuum. So the vacuum inside the vacuum tube is a hard vacuum, which means just like outer space. So you have extremely few gas molecules inside the light bulb, and when an electron goes off from the cathode, it flies in space. So basically, a vacuum tube is a particle accelerator. So it accelerates electrons. And the transistor is not a particle accelerator. It's a breaker. It's like a variable resistor. And so how do vacuum tubes achieve this phenomena? First of all, it all happens in a vacuum, but to do that, what we need to do is make the cathode. So this is the cathode, either written, usually shown by a letter K or letter C. We have to heat it up. We have to make it really, really hot. How hot? Between 900 to 1200 degrees Celsius. So we have to heat up that rod. You see those two that's running in the center, it has to be around 1000 degrees Celsius. And when it reaches 900, then if we add voltage here, then the electrons that are part of this metal, they will be attracted to the plate. And the higher the voltage we apply to the plate, the more the electrons will be attracted, and the faster they will be flying. So essentially, this is a particle accelerator, and you can make it a stronger particle accelerator if you increase the plate voltage. So that's why in vacuum tubes, it's not unusual to see a 500 volts supply or even more, because the higher the voltage, the higher the electromotive force, the faster your electrons will flow, and that will translate to a more dynamic effect. So if you want to increase the dynamics of your vacuum tube amplifier, then increase the plate voltage, so it will be more dynamic. And this control grid is required to have a negative charge, so that it's in the path of these electrons, and when that basically shields this electrode from the cathode. And when we apply the music signal to this electrode, then based on the music signal, the electrons can move to the plate, or they are held here, move more, held here, move more, held here. And as a result, we will have electrons that are accelerated to 500 volts. So a vacuum tube will generate us extremely fast, very high voltage, very high energy electrons. In the case of transistors, the voltage is very low. So there are some transistors where we apply only 12 to 14 volts. That's the majority of the transistors. They run on this voltage. And when you look at more premium transistors, they are maybe like up to 28, 30 volts, and which are used in audio, and also in a real life in non-audio. For example, like the Shinkansen, like the super fast trains in Japan, and in other areas of industry, there are transistors which can take up to a kilovolt, like 1000 volts, or even like 10,000 volts of voltage, but those are not used in audio. They only use these low voltage ones, so either like 14 volts or 28 volts. And that's what you get, electrons chugging at the speed of 28 volt. And basically this range like going from 0 volt to 28 volt. Let's see the example of a premium transistor. So let's go with 28 watts. So we have a voltage range between 0 to 28. So this is our dynamic resolution. So we can see the music translated into electrons flowing from 0 to 28 volts. However, there's something that is called as nonlinearity. So it means that all the devices, so if we look at this, so this would be the input signal, and that's the output. So as we increase them, we should expect this, that with greater input you are getting greater output. However, due to the nonlinearity, when we are at the small signal range, it falls off, and we are not getting a linear region there. And when we are at the peak power, then it cannot handle anymore and it will peak out. So this region that's in between the two, here, right there, that's called the linear range. And that's what is useful for your audio. So let's say for a transistor, this linear range would be maybe between 3 volts to 25 volts. So basically we have a 23 volts working range that's useful for your audio. And that's the resolution you are getting from a transistor. In the case of a vacuum tube, let's calculate with a 500 volts voltage on the plate, which is pretty common for vacuum tube amplifiers. There are some that run at considerably lower voltages, but there are some that run at even 10 times this voltage. So let's just take 500 volts. In that case, when we plot input output, if you take off the lowest range, let's say the lowest 50 volts and the highest 50 volts, we have a 400 volts linear working range. So in case of our vacuum tube, we have 400 volts resolution compared to the transistor's 23 volts resolution. When you look at that, that's like a more than one order of magnitude between the resolution of these two devices. So that's why vacuum tubes are technologically a much better solution for looking at audio signals, because their linear range, their working range is tremendously higher than that of a transistor. And there's no changing that. The only changing that would be if we would have a transistor that's running at 500 volts, but that costs much more than these tiny transistor, low voltage transistors. So that's why manufacturers are not using it, because the only point that transistor came to being is because they look at the size. This is a fraction of the size, fraction of the weight, fraction of the cost, and that's why that's all the niceties about transistor amps. If we want to increase this to be able to handle 500 watts, then we would be already forfeiting much of the practical benefits that transistors give us. So that's why audio companies hold on to the low voltage transistors, which are super limited devices compared to the vacuum tubes. But even if we had like a transistor which is like a much more bigger than this and capable of handling 500 volts, so it would give us also a 400 volt working range or so, even in that case it would be still handicapped compared to the vacuum tube, because in the case of the vacuum tube there is no physical barrier for the electrons. So the electrons are flying in vacuum. There are no hard barriers there. There's only a magnetic effect of the grid that's slowing them down or letting them speed at full speed. while in a transistor you have these two ugly barriers and all those reactions, chemical reactions happening there. It's not nice. It's like a battery's electrochemical noise added to the system. So that's why for low level signals transistors lose all the time against vacuum tubes, and dynamic range they lose really big time as well. And as a consequence, what people do with transistors is they employ a lot of feedback loops to correct their behavior. And however, that causes lots of problems. So for vacuum tubes, you do not need to employ that many feedback loops. If you want, you can use vacuum tubes without any feedback whatsoever. With transistors, it's extremely hard to do. There's very few people who are using low feedback transistor designs, but it's not something that can be done on the thousands of amplifiers. It's really something truly specialized. So I hope this helps a little bit in understanding what's the difference between these two, and we'll continue. Thank you, and bye bye.